What? Can you see my screen?
Yes,
It's
yes, it
coming.
is coming.
The only problem is that once I have this up on Google Meet, I can't see you. But let's hope it
We
works.
can see you.
Good, wonderful. That's a better way.
This is the drawback of Google Meet.
Yeah, that's a
The
problem.
presenter cannot see himself and the participants.
So let's. What I want to do today is talk about black holes, and I'll bring out a couple of things that might be interesting to everybody, particularly to engineers. But I also acknowledge the fact that this is a very general audience. I can see physicists in the audience. I can see people who are not directly related to um, the study of black holes in general. So what I will do is I will start at a very basic level. So if, for example, you know a lot about what I am saying, please bear with me, because I hope there will be something for everybody. And this is very topical, of course, because this year we got this general area got the Nobel Prize, and I'm going to talk about some of that work as well. And I also talk about what we will do in the future to look at these black holes. So just to introduce where I work at this institute called the Inter-University Center for Astronomy and Astrophysics, which is in Pune. And several people, I'm sure, have been here. I can see Raychoudhury there, who's one of our associates. So this was built about 30 years ago by Professor Jayant Narlikar. And it is essentially set up as a place where, because in the 1980s, even in the 1980s, astrophysics was not a popular subject in India. And it was felt that in order to bring it in to universities, there needs to be a center where people can come together, particularly people who work in colleges and universities. And right now we have almost 200 such associates who are teachers in universities and colleges who come here to work and work with each other. In fact, this year I can see that the number of papers written by associates in astrophysics exceeds the number of people written by us who are members of the institute. So it is actually a wonderful place where people can interact. And black holes actually is a very general theme of research in many parts of what we do. I say this in this to this audience because a lot of you also are teachers in colleges, universities, or will be, and it is good to know that such a facility exists under the UGC, where one can actually have access not to national other people working in the country only, but also to international facilities. And I will talk about a couple of things later on today where you can see how we build access to international facilities for the Indian community. Okay. So let's talk about black holes. Black holes in general, as you know, have a very bad press. People actually do horror movies. Science fiction talk about black holes is really not very friendly. They are out there to get you. They are no force from this world can stop it. As you can see, the famous Disney movie called The Black Hole and things like that. And I hope that at the end of this talk, you will get to go away with if you haven't already, go away with a notion that black holes aren't really that unfriendly. They are pretty interesting objects. They keep to themselves. If you leave them alone, don't go very close. And they are not there to get you, as the science fiction movies tell you. So what is a black hole? Let's start from, as I said, from the very beginning. We start from Isaac Newton. This is something that everybody reads in school. Newton's laws, Newton's theory of gravitation, and Newton's theory of dynamics all came from trying to address the question. Essentially, Newton was prompted by the question, why does Halley's Comet come back every 75 years, right? And to look at why that happens, of course, Newton had started thinking about it long ago. In fact, Newton's idea of gravity, as you know, came in a situation which is very similar to the pandemic year now. In fact, when he was an undergraduate at Cambridge University was shut down for 1.5 years because of the plague pandemic. and he had to go home. So here was Newton, 22 years old. He had to go home. His mother didn't want him back home. His mother had remarried and moved away somewhere. So he went and stayed with his mother's sister, aunt. Aunt had a nice apple garden. And as you know, he spent the entire year and a half with his aunt. And during that year and a half, he discovered the binomial theorem. He invented differential calculus. And also he had this idea of gravity. And the whole theory of gravitation, of course, later on he said it came from the apple falling, etc., while sitting under the apple tree. But the idea is as follows. He said that there is this force that is universal. It acts between anything that has mass. And so it is the same force that the Earth exerts on the apple that the Earth exacts on the moon, and the moon exacts on the Earth, and the Earth goes around the sun due to the same, it's universal. Now, today, it is very difficult for us to understand how revolutionary such a concept is, because the entire Western philosophy on which the science is based, of the philosophy of Plato and Aristotle and everybody else, even all the way up to Copernicus, always said that the heavens are made up of something else. And anything that is applicable on Earth doesn't apply to the skies. It is really from Galileo and then Newton that we have started in the history of science to believe that actually what we see in our lab on the Earth also be seen in the rest of the universe. So Newton, talking about the laws of universal gravity, is actually a wonderful and very unusual thing. Can I ask everybody else to mute their audio, because I'm getting a lot of feedback from others. Just please ask questions at the end of the talk, and please mute your audio. Thank you.
Mute yourself.
Or actually, the host can probably mute them as well.
Yes, I've done that.
Thank you. Okay, so from Newton's very interesting idea of gravity comes this concept of escape velocity, which also we learn in school. And it's a very simple formula that in order to escape from the gravitational force of a particular object like the sun or the Earth, you have to have a particular minimum velocity, and this minimum velocity corresponds to a kinetic energy that needs to overcome the potential energy due to the gravitation. That's the idea. And so this, as you know, velocity is half mv squared, which is why this formula comes very easily to gm over r. Now that 2 gm over r square root actually tells you what the escape velocity will be. So something that is very massive but has a small radius will have a higher escape velocity than something at the same mass but a bigger radius, right? So you can understand black holes from classical gravity, which is Newtonian gravity, in this way, that if the escape velocity from something is greater than the speed of light, then nothing can escape from this particular object. Right, Newton, of course, did not know this. In Newtonian gravity and Newtonian mechanics, there was no upper limit to the speed. But later on, in the 20th century, from Einstein, we learned that nothing can go faster than the speed of light. If you combine these two ideas, then you can figure out that that you really cannot escape from something where the escape velocity is faster than the speed of light. But even during Newton's time, people realized that if, for example, something has a very, very high escape velocity, you cannot escape from it. Right? So that is essentially the classical description of a black hole. You take your escape velocity, which from the Earth is about 11 kilometers per second, 43,000 kilometers per hour. So you can see that you cannot drive a car that's so fast that you can break free of the Earth's gravity. I mean, the police will catch you first. And then, as you can see, the Earth's escape velocity is pretty high, and this is why the sun's escape velocity is pretty high, so the Earth cannot escape from it, and things like that. And so then, if you look at a mass and then you decrease its radius, because it is 2 gm over r, if the r is small enough for any mass, you can make this criterion work, which means that you can turn anything into a black hole, including you and me, if we can take this mass and shrink it such that the r is very, very small. Right? So how small? So you can have a dark star if you can take the speed of light and put that in to that formula, this formula that I talked about, and see that V escape becomes C, right? So actually you can't do that, because now we come to the real situation where you have to, if you want to make that calculation, you have to talk about things that are going very fast, very close to the speed of light, and then Newton's laws actually are not very complete, and you need a modification to that, and I'll come to that in a minute. But actually what happens is the formula that comes, if you do it properly using our modern idea of gravity, which is due to Einstein, then you get this particular formula, which tells you that which is called the Schwarzschild radius. If you take anything that has a mass m and you shrink it to this radius, right, this size, so 2gm over c squared, then that becomes a black hole, which means that the escape velocity from it becomes the speed of light. So for the mass of the Earth, it is less than a centimeter. So you can see how difficult it is to make a black hole. You can't really squeeze the Earth to less than a centimeter in radius. And so sometimes, you read in the newspapers that, oh, the LHC is going to turn on their experiment, and it's going to turn the Earth into a black hole or whatever. You can see how difficult that is. It is not really possible. For the sun, a star like the sun, that particular radius is about 3 kilometers. Is that possible? So that it was the question essentially. So even in Newton's times, people were worrying about this, even though they did not have the exact formula, but from the concept of escape velocity, they were worried that you will probably have stars that have the combination of m over r, such that there will be things that cannot escape from it. It will pull things in and you cannot escape from them. That's the idea. But so what happens is that, so we take Newton's idea of this gravity, and as I said, if you really want to apply this to this extreme case, black holes, where things are traveling very close to the speed of light, and the force is so high, it actually requires kinetic energies that are this high, then we know that Newton's laws actually won't work. And this Einstein started thinking about at the beginning of the 20th century, about 100 years ago. And Einstein, of course, from the very beginning, from his very young age, had started thinking about some anomalies in Newton's description of gravity. This whole thing about actually gravity is a force, which is a pull between two objects, which acts along the line. It's a vector, right? And so this, even at the age of 14, 15, Einstein was writing essays saying that this really cannot be true. And why? And that is because, for example, he was thinking of an idea of two things traveling very close to the speed of light. And he was asking the question, how, while they're going so fast, how does this object know which direction the force is coming from, right? Because by the time this object has known that this other object is pulling it, the other object would have moved somewhere else, right? In Newton's formulation, the information traveled between two objects at an infinite speed. So there is no time lag. But Einstein has been, at that time, working on this theory that no information can travel faster than the speed of light. So once you acknowledge that, then you start worrying about what is this nature of gravity? How can you actually have a long distance force acting between two things? How do they communicate with each other? So Einstein came up with a very interesting idea, and that is that actually Newton's formulation is all right, but you have to generalize it and look at it in a very different way physically. So gravity is not a force. Gravity actually comes from as a result of matter distorting space itself, right? So the idea is that that matter itself distorts space, and then space, this distorted space, then leads to things moving in distorted space in orbits that look like as if gravity is a force, right? And so I'm going to elaborate a little more on this in a minute, but just tell you the history of how this happened. Einstein in 1915 worked out this theory that we need to look at gravity in a very different way. So Schwarzschild, within a few months of this theory, had actually solved Einstein's equations in the case of a spherically symmetric system. Schwarzschild actually took this paper, which had come out in Germany during the war, so the English-speaking world had not actually seen this yet. Germany was fighting in the First World War with the English-speaking world. And so, but Schwarzschild, being a professor of mathematics at the University of Göttingen, had this, and he had gone to war with the German army in the Russian front. And he was, in his notebook, essentially solving Einstein's equations, and he managed to solve it and come up with this famous formula that I just showed you. But he also solved it to show what the shape of space-time would be around a spherical object. And he sent a letter to Einstein saying that I've solved this, and then he died in the war. So Einstein published Schwarzschild's paper after his death. But he actually worked out what we call the Schwarzschild metric, which works out what happens to space-time around a massive object. But and as a result of that, you get this famous formula of the size of a black hole, for example, where if something enters that radius, then it cannot come out. But how would you figure out how to make this into a black hole? I said, if you take something like the sun, to turn it into a black hole, it would be 3 kilometers small. How would you make that? And the person who showed us how to do that is Subramanian Chandrasekhar. Chandrasekhar, in the 1930s, worked with Paul Dirac in Cambridge, and as a PhD student, and even before actually reaching Dirac, he had formed a very good idea of how stars can collapse and how stars can, very massive stars, can collapse to form compact objects like white dwarfs, neutron stars, and black holes. And from the work of Chandrasekhar, who was the first person to apply quantum mechanics to stars, we now have an idea of how these very compact things can form from stars. So that is the idea of Einstein. Einstein's idea is that if you have a massive object like the sun, then around it, space itself curves. And the Earth is moving around the sun because it is trapped in this curved space-time. It is not because there is this invisible string that is pulling each other. And this we don't learn in school. We learn in school the Newtonian way, whereas this is really the real representation, the most general representation. And it turns out that for velocities that we are used to, Newton's laws are absolutely fine, they work very well, but the concept actually really breaks down even if you consider the sun and the Earth system. You can see that space-time is bent a little because of the Earth, and it goes around because it's trapped in this. So then you can see the more extreme case, and the extreme case is what happens if this sun now shrinks to a very, very tiny size, like as I said, a few kilometers. Then, because of the shape of the space-time around it, it is going to be very, very bent, and the bend will be such that it will create an extreme curvature in space-time. And so the Schwarzschild radius I talked about, which is actually the radius of the black hole, is called the event horizon. And that inside the space-time is so bent that if something, including light, goes in there, it cannot come out again. So this is the idea. This is the geometrical idea. And in the middle, right in the middle, is something called the singularity, which is where space-time actually becomes so bent that a mathematical description of that becomes very difficult. And so this year's Nobel Prize essentially came for the work that was done to kind of mathematically characterize the singularity, to show that the singularity is a very natural thing that comes from such calculations. One of the things that the Nobel Prize was given to Roger Penrose this year. Now, I want to take a little break from this narrative for a couple of minutes and talk about the relevance of all this to Indian science. over the last 100 years, ever since Einstein published the theory of relativity, the general relativity has been extremely popular as a subject in India, even though astrophysics in general wasn't very popular. And that is because some of the greatest mathematicians that were around took up general relativity as something that they can work on. And I just wanted to highlight a couple of things. So for example, if you look at the journal, General Relativity and Gravitation, in a few years ago, they published from 1915, that is the original paper of Einstein, for 50 years. In 50 years, what are the most important 24 papers that were published in general relativity in the whole world, right? This was a compilation volume. And it is very interesting that out of those 24 papers, 5 papers were from India. And just think about that. Just think about it's worldwide. On the top was, of course, the famous paper by Amar Kumar Raychoudhury, which set out the Raychoudhury equation, which we talk about. And of course, Amar Kumar Raychoudhury was our head of department. As Shushmita said, she and I studied in the presidency in physics together, and our head of department was Amar Kumar Raychoudhury. And later on, after retiring, he actually worked quite a bit in Jadavpur University, setting up the Relativity Center there. But he published this paper when he was a lecturer at Ashutosh College in 1955. Then, most interestingly, before Amar Kumar Raychoudhury, the people who set up the relativity research in India were in 2 or 3 different places. One was, of course, V.V. Narlikar, who came back from Cambridge. He was a student of Eddington, and he set up his school of relativity at the Banaras Hindu University. And his student was P.C. Vaidya, who also did quite a lot of amazing work. As you can see, P.C. Vaidya's papers, 2 of P.C. Vaidya's papers are in this, this compilation. And he was then the Vice-Chancellor of Gujarat University in Ahmedabad later on. But another very interesting group was in Presidency College in Kolkata. This is before Amar Babu. And this is N.R. Sen. N.R. Sen actually used the general relativity to work out the stability of stars, stability of the universe, stability of general systems, and then he had one of the most important papers that we find in the history of relativity is about how a star collapses to form a compact object. And this is very strangely written by this man called B. Dotto, who has written only 1 paper in his life. There's no other paper written by him. And this was published in German, in a German journal, and essentially forms the basis of our knowledge of how things collapse, right? Now, very little is known about it, and I have tried to trace B. Dotto to find out what happened to him. And a lot of people have been asking this question. So I dug up a lot of papers while I was teaching in Presidency College, and found that actually, sadly, while he was a PhD student of N.R. Sen, and during doing his PhD, after writing this paper, he actually died. He died after a hernia operation in Kolkata Medical College Hospital. And the more interesting thing is this B. Dutt, if you can see this D-A-T-T, is a signature spelling of the surname. Not many people spell their Dotto that way. And you guessed it right, the only other person you've seen spell it that way is Swami Vivekananda. And B. Dotto's name is actually Vishesha Dotto. And he was Swami Vivekananda's brother's son, lived in Shimla Street. And so that's all I've got from now. And I'll try and trace him, but very little is known about him. But he wrote this absolutely classic paper, which is now one of the bases of how things collapse in spherical systems. And I said that Chandrasekhar worked out how stars turn into black holes, but you have to use a lot of these famous papers in order to figure out how these things happen. So I just wanted to make sure people know That's NR Shen and Vigat. So together in Presidency College, this is before Amol Babu came to the scene, and Amol Raychoudhury's famous paper, which leads the whole field and brought up this famous equation called Raychoudhury equation, which allows you to incorporate things like stress and strain, things like torsion, etc., into a general relativistic description. And this is very important because this laid the basis for Penrose and Hawking to do their work on singularities of gravitational collapse. Hawking, in his PhD thesis, used this equation from this paper and called it the Raychoudhury equation. And later on together, and they went on to write this series of papers, for which later on last year, Penrose got the Nobel Prize. Hawking sadly, of course, died and could not get the Nobel Prize before that. So, so that is, kind of the link to essentially the work on relativity that's been done in India, and particularly in Kolkata, and the way black holes are mathematically derived. And I'm not going to go into more about this because today I'm going to talk about how to actually find these things. And I spend the rest of the talk talking about how do you actually find a black hole. So how big is a black hole? As I said, a black hole is, if you look at the sun, which is compared to the Earth, pretty big, but for it to become a black hole, it would have to be something that's much smaller, almost the size of Jadavpur, right? So, so think about how that would be. So here you are, you take that formula, the Schwarzschild radius, and I said 2gm over c squared, and you have to get a star down to 3 kilometers. How would you do that? The reason we cannot see a black hole is that that's what a black hole looks like. This is a close-up picture of a black hole. A black hole is black, which means that nothing comes out of it. And the challenge of finding a black hole is to figure out the surroundings of a black hole. Because almost everything that we see in the universe comes from light or some other kind of electromagnetic wave, and now gravitational waves that come from some object. So you're seeing me because I have light bouncing off me, going to you in a very complicated way. But without this light, you wouldn't be seeing me. But if nothing comes out of a black hole, then there is no way you can see it. So how would you do it? The thing is, the black hole is so extreme, its gravitational effect is so extreme that it is very difficult to cover it up. That's the whole idea. And so I'll come back to it in a minute. So we have 3 different kinds of black holes, we think. Actually, there are 2 different kinds that we are sure about. There are some black holes that are of the order of the masses of stars that we see around us, which means that they are a few times the mass of the sun. The most massive star in our galaxy that we know of is about 100 times the mass of the sun. We don't know of any stars that are more massive than that. So since black holes come from stars, we're thinking of black holes which are in the range of, say, 1 times the mass of the sun to 100 times the mass of the sun, something like that. And then there are things called the supermassive black holes, which are about 1,000,000 times the mass of the sun to 1,000,000,000 times the mass of the sun, in that range. Very, very massive, right? And we don't know where they come from, though we are beginning to understand that. And so there is always, for a long time, so we are sure of these. And I'm going to talk about two or three different ways of finding these things today. This is the whole point of today's presentation. But only recently, and people have asked this for a long time, how do you go from a stellar mass black hole to a supermassive black hole? Why isn't there anything in between? You have, say, 1 to 100 times the mass of the sun, and then 10 to the power 6 to 10 to the power 9 times the mass of the sun. What happens to 10 to the power 3, 4, 5? Why aren't there black holes of that in this range? And they have been missing. And only recently, in the last year or so, have we started seeing black holes that are in this range. And so that is very interesting. And so this is a new thing that is emerging. So here is our galaxy. We live in a galaxy. in our galaxy is called the Milky Way. This is what it looks like. Of course, this is not a picture because you can't take a picture of our own galaxy. The universe is made up of galaxies. So our galaxy is can you mute me? Our galaxy is there's a feedback. Our galaxy is a very flat object, and it has about 10 to the power 11 stars. Our sun is a very small star, which is in this disk of this galaxy. The galaxy is very flat. It's like this sideways, and if you look at it from top, you will see that there are these nice spiral structure, and the sun is not at the center, but it's offset about 25,000 light years away from the center of the galaxy. Right, 8 kiloparsecs is about 25,000 light years. So it is offset, and so when we look at the sky, we are looking at the stars that are essentially in this little thin segment of the galaxy, the disk. Right, all the stars we see with our naked eye in the galaxy are essentially in that little thin segment. Right, we're looking, and of course, if we look towards the center of our galaxy, we will see a very thick band of stars, and that's why it's called the Milky Way. In Indian languages, we call it the Akash Ganga, and so it's a river in the sky, and that is why, and that's because there is this. So if you look through, look at the sky, you will see a whole band there. Now, we can't really see the center of our galaxy very well from India because the Earth blocks it. You really have to go to the southern hemisphere to look at Sagittarius, which is the constellation in which the center of our galaxy is. But you can see that there's and then in the middle of this galaxy, as I said, is there a supermassive black hole. Center of all galaxies has one supermassive black hole that is at least about 1 million times the mass of the sun, right? So we, in order to find these supermassive black holes, can try our own galaxy first. And this is the subject of this year's, the other half of the Nobel Prize. Not only finding, but measuring the mass of the center of that black hole, that central black hole. So I just wanted to point out there are two problems with trying to detect the central black hole of our galaxy. One is that if you look through the plane of our galaxy, you will see that there's a lot of black dust in there. Yeah, and that dust comes from the fact that this is the stuff that did not get into the stars, or they come out of the stars as they evolve and die and things like that. And so that blocks a lot of the visible light, the light that we see things in. So if you want to see towards the middle of our galaxy, you have to see through that dust. And the second problem is that if you really want to find the neighborhood of the black hole, you really have to see a very high resolution. Now, as I said, you cannot really find the black hole directly, right? Because it's black. So what you can do is you can look at stars that are around the black hole. Just like you can, if you look at all the planets and you didn't see the sun, you can measure the mass of the sun by looking at the orbits of the planets. Because the sun is pulling the planets and the planets are going around the sun. And so from the orbit of say the sun, from the orbit of the Earth, you can measure the mass of the sun. Simple. So here, for example, and this is a real picture of looking towards the center of our galaxy. And here we're looking at in the infrared. So we're looking at a wavelength of 2 microns. And so at that wavelength, the dust becomes transparent. So one of the ways one can look at this is that you can actually look at, and so you can see lots of stars around there. And that's where the black hole at the center of our galaxy is, which you don't see, Sagittarius A star, right? So the idea now is that what you can do is you can measure the motion of these stars because they will go around the black hole. And so year after year after year, not only year, day after day after day, you can try and see whether you can see the stars move, right? And because the stars around the black hole would be moving very fast, right? Like that. So this is essentially what the problem is. Now, the main problem, and this is where I think engineers come into the picture in a big way. The main problem of trying to find these stars near the Milky Way center is the fact that stars twinkle. So, you know, the stars twinkle. If you look at the stars, they twinkle. And why do they twinkle? And that is because it comes through the entire atmosphere. Starlight comes through the entire atmosphere. And at every point in the atmosphere, the pressure, temperature, and density is different. And it also always varies of the order of a second or even faster. It varies because there's so much heat exchange going on between the various layers of the atmosphere during the day and during the night. And so the air is always moving, so the refractive index is changing. And so when the light comes through, it is refracted in various different ways. So for example, if this, you can see a speckle like this is an image of a star, it will move very fast at the focal plane of your telescope or your camera. And so if you're taking an exposure, which is a few seconds, a few minutes, a few hours long, the image will be blurred. And it gets blurred to about a second of arc or more in normal cases, even in the best places on the Earth. And that is called seeing. But the stars that I showed here, that are very close to the black hole, are the angular distance is about 1/100th of an arc second. You know, 3,600 arc seconds make a degree. And the moon, for example, is half a degree. So think about how close you have to get on the sky to these. How do you do that? And so this is an engineering miracle that has happened now. And that happens in these telescopes that are used to observe these things. So these, for example, are the two of the largest telescopes on the Earth now, the 10-meter, two 10-meter telescopes, the Keck telescopes in Hawaii, which were used to make this observation. And if you look at the telescope is 10 meters across, but it's actually made up of 36 different mirrors, hexagonal mirrors. They're put together. Now, because this entire thing can be computer controlled now, and the mechanical structures and the electrical work, the electronics is so exquisite that the paraboloid shape that this mirror makes, the 36 segments make, can be moved, and the shape can be changed of the order of 1/10 of a second, right, in order to compensate for the twinkling effect of the atmosphere. So there's a separate telescope that is actually observing a point object, and it is finding out how that speckle is moving, and it's feeding that information into the system that is the mirror, the primary mirror. And as a result, it is programmed to change the shape of the mirror in real time to compensate for that. And this is called adaptive optics. Adaptive optics is an amazing subject. And here in IUCA, we have a wonderful lab of adaptive optics, and we build adaptive optics for small telescopes. This is, of course, one of the reasons the Nobel Prize was given this year, was that the biggest telescope in the world can do adaptive optics. And you can see essentially the wavefront that comes from stars can be made straight, such that something that is blurred, say two objects are blended together, can be decoupled. And this is exactly what has happened in the center of our galaxy. That's where the black hole is. And you can see without adaptive optics, even with the biggest telescopes in the world, the resolution would be such that it would be completely blurred. And on the right-hand side, it shows you what the galactic center is at 2.2 microns, how exquisite the resolution is, and the black hole is somewhere there, and you can see the stars very nicely around it, right? And the separations of points that you see there are of the order of 1/50th of an arc second, right? And so you can actually see these things. The two people who did this got the Nobel Prize this year. Andrea Ghez' group in UCLA used the two Keck telescopes to do this. The same project was done from the 1990s by Reinhard Genzel using the 4 very large telescopes in Chile. And they both looked at the galactic center and did this campaign for this big white star is, that's where the black hole is. You don't see the black hole, right? But you see all these stars around. And you can see the scale of this is 1/10 of a second of arc. And the resolution of these telescopes can go up to 1/50th to 1/100th of a second of arc because of this adaptive optics. Amazing engineering feat. And you can see that they have, right, you can see the year here, right from 1995, this is Andrea Gez's work, they can map out orbits of these stars. And you can see this star, the yellow one, which is my favorite one, S2. See this again, and you will see starting from 1995, every night a picture has been taken to see where these stars are. And many stars have now gone around the black hole. This one has a perfect ellipse that has a period of about 15 years. And from that, you can, so the two people actually published papers right from the mid-90s onwards to actually map out these stars. And from them, you can figure out what the nature of this central object is, where the black hole in the middle of our galaxy is. You can do this with Kepler's third law, or relativistic version of Kepler's laws, and they measured the mass of the black hole to be 4 times 10 to the 6 times the mass of the sun. So 4 million times the mass of the sun. And you can see that from, just like Kepler's laws will tell you, that the central object that's pulling these stars around, this is from S2, is at the focus of the ellipse. And it is the size, the star gets so near that from the size you can see that it can only be a black hole and nothing else really of that mass. So, so for establishing the black hole in the middle of our galaxy, the Nobel Prize was given. And it's not just because they drew this picture, the entire technology that went to make this happen is very, very interesting. So I'm going to, in the remaining talk, so I'm asking the organizers, I have about another 15 minutes or so?
Yes, sir.
Yes, good.
There is no time limitation. You can.
Good. So what I'm going to do is, so this is one way I said that we can find supermassive black holes, which is in the middle of our galaxy. Now, let me see how we can find, if you look at our galaxy, more than 50% of the stars are in binary systems. They are going around each other. Our sun is a lone star, which is actually unusual. Jupiter could almost have become a star. It failed to become a star, and you could have had 2 stars. We could have had 2 suns in our, but actually most planets have 2 suns in their sky, because, as I said, more than 50% of stars are in binary systems. I don't know whether you remember Tatooine being such a system in the Star Wars universe. So, so say there are 2 stars, and one star is smaller than the other, typically. Now, in astrophysics, we know that stars evolve. What happens is the stars spend most of their life, they live for billions of years, and they spend most of their life, I say life, but yeah, so active phase, creating light in the middle of the stars through nuclear fusion, right? And so at some point, the material which is creating the light because of nuclear fusion is finished, because it is all over. And so at the end of that I will refer to as the death of the star. The star dies. How does it die? The equilibrium that holds the star together is lost, because.
Hello.
Am I back?
Yes, yes, sir.
Yes, sir.
I don't know what happened, but the
Maybe due to internet problem.
Your presentation.
Okay, let me just try the presentation again. Is this working?
It's coming, sir. Yeah.
Yes, sir. We can see that.
Okay, good. So I was talking about 2 stars. Now, 2 stars going around each other. Now, normally stars evolve, and at the stars end their life, as I said, when this equilibrium goes, and the stars expand and then slowly lose their outer layers. And if it's a very massive star, it explodes. Okay. So can you hear me now? Is that all right? Okay.
Yes,
right.
Sir.
So now the lifetime of a star in this phase depends on its mass. So the more massive stars evolve faster. Yeah, because their nuclear reactions also are faster because of the heavy gravitational pressure. So imagine there are 2 stars in a system that are going around each other. So the right-hand one is much bigger, and so it will evolve fast. So it does what I just said. Outer layers it disperse, it explodes, and the inner layer collapses, and it collapses to form a black hole, like Chandrasekhar had predicted. And as I said, people like Enashen and others had worked out how that collapse will happen. So it forms a black hole. Now we have a normal star and a black hole. They're going around each other. Okay. Now, very soon, not very soon, but many millions of years later, the other star will also evolve. And so what will happen is it will become larger and larger and larger, because its equilibrium is now lost, and so it will become very large. This is called a red giant. And as it becomes larger and larger, you can see that the outer layers, the gravitational pull from the star outer layers, becomes less and less and less because it becomes very large. And the gravitational pull of the black hole on the outer layers might be actually much more. So what will happen, that mass will start falling on the black hole. Now, this mass from one star falling onto the black hole, which is the companion of this star, cannot fall directly in because it has angular momentum, and angular momentum cannot be destroyed. So what will happen is that it will go on going around the black hole. So it will form a disk, and this is called an accretion disk. It forms around, so you can't see the black hole. The black hole is black. I've put it gray in here, but there's a disk of matter going around the black hole, and this becomes extremely hot because the gravitational potential energy of the black hole is very high. And anything that is just outside the black hole gets very, very hot. It actually gets as hot as 10 to the power 7 degrees. And at 10 to the power 7 degrees, most things emit X-rays or gamma rays. X-rays mostly. Because if you look at a black body curve, that's where the peak of that X-ray of the radiation is. So this is an artist's impression of this now. You can see the black hole is the middle. There, you can't see the black hole, but who cares? You can see the accretion disk of the matter that's falling into the black hole right outside, and it becomes so hot, it's emitting X-rays now. So you have to, in order to find these black holes, the stellar mass black holes, which are in binary systems, you have to have an X-ray telescope and take X-ray pictures, right? So what do you mean by X-ray telescopes? So X-rays, as you know, this is the electromagnetic spectrum. The very tiny bit in the middle is the visible light, which is of the order of, say, 10 to the power minus 6 meters or less in wavelength.
You are disconnected, sir.
I can see that I could see the camera go off. Let me try again. I'll finish in about 10 minutes, but I don't know why this is happening. My
internet connection may be unstable.
no reason to, but maybe there's some power problem happening. Okay, let's try it again. An excellent observatory, and why is it so unusual? It's unusual because it has this very unusual orbit. You can see that it's a 64-hour orbit. Hello?
Yes, your screen has now.
Yes, sir. Now we can see it clearly, sir.
Yeah. Okay. So can you see this? Yeah. So the Chandra X-ray Observatory has this amazing orbit, which is about 54 hours. And it is built such that it spends about half the time away from the radiation belts that are around the Earth. And so can observe I'm sorry, I don't know what is happening.
Okay,
Your slides, please.
My speed test shows that my internet is running all right. I don't know what is happening. Can you see my slide now?
Yes.
Yes, sir.
Let me wrap it up soon. So let's see if I can I switch off my camera? Maybe that can help. And just keep the slide.
Yes, sir.
Okay. Can you see my slide now?
Yes, sir. Yes, sir.
Right. So the interesting thing about X-ray telescopes is that you cannot actually have anything that the X-rays come at is more than 2 or 3 degrees. You can see from the surface, it will go right through at keV energies. Right? This is the critical angle above which the X-ray goes right through. So think about how you can focus a light without having a mirror that can do normal incidence. So this is what happens in X-rays, and it's wonderful that such a mirror system could be built so that it can give you sub-arc second resolution in images, and which Chandra does, which is the same kind of resolution as the. Whoops, am I still there? No.
Yes, sir. Yes, sir.
Okay.
It's fine now.
Right. Please tell me if you lose me again. Okay.
Yes.
And so this has now been done, and this high resolution imaging can be done in X-rays right now, and you can see that that is why the Chandra Observatory is 5 meters long, because the way the X-rays are focused is that they're focused with very tiny angular deviations, the rays themselves, and go through this entire system, and they can also be nested because they are grazing incidence things. So so this is why, for example, the Chandra X-ray Observatory, this is a good example. The mirror is so long, and it goes all the way through, and
Hello, sir.
yeah, I need to finish my talk because this is I don't know why this is happening. Okay. Can you see this picture now?
Yes, sir.
Okay. So in this particular picture, you see a lot of stars in the galaxy, and this is a picture taken in normal light. Now, everything that you see in normal light will be a few thousand degrees hot. Our sun is 6,000 degrees hot, and so between say 2,000 to 10,000 degrees or so, the peak of the radiation from a star emits normal light. Now, the X-ray picture of this particular galaxy on the same scale is this, the blue thing that you see now. And this is work done by the Chandra X-ray Observatory seen on now. This is an entire X-ray image taken at around 2 to 10 keV, that kind of energy photon. Now, what you see here, everything that you see here is at least 10 to the power 7 degrees hot. 10 to the power 3 degrees hot, 10 to the power 7 degrees hot. And what do you see in this picture? You see the central black hole, which is a supermassive black hole. You see it glowing very, very big. You see a lot of gas coming out of that black hole, not off that black hole, but near the region of the black hole in the form of a jet. But more interesting.
You're lost again.
Yes.
I really don't know why my connection is dropping.
Sometimes it occurs due to the internet.
It never happens. It is very interesting. Anyway, so can you see this now?
Yes, sir.
So there are two projects I quickly wanted to talk about that is in this relevant to this, but it's also relevant to the people who are listening today. And because, I mean, say 30 years ago when I was a student, we thought that if you wanted to do big, very big, large-scale experimental projects, you really had to go abroad. Now, India, not only on Indian soil, but elsewhere, India is involved in leading roles in building some of these today. The 30-meter telescope in Hawaii, and the LIGO India Observatory, which will be built in India, and the square kilometer array, of course, which is being built all over the southern hemisphere. India is part of that. The 30-meter telescope in Hawaii is going to be one of the largest telescopes in the world. It will take 10 years to build, and it's got 492 mirrors. And it's exactly how I showed the Keck telescope to be, which had 36 mirrors, but a much larger version. And that is going to be built probably in Hawaii. It's still being, there are certain problems with the site itself. The 5 countries that are building it are America, Canada, Japan, China, and India. India is 10% of this particular project. And Andrea Ghez, who you saw, I sit with her in many committees because she's part of the US delegation building this. And of course, she's very interested in building a much larger Keck to do the kind of work she does. the interesting thing is now India is not just paying the money. India, the 80% of the Indian contribution to the 10% of this telescope is actually building these things. In fact, if you look at the mirrors, 100 of those mirrors are going to be built in India. The mirror support structures for all 492 mirrors are actually built in small engineering firms all over India, and they're building the various mechanical and electronic parts of this mirror. And the entire software of the observatory is being written in Pune right now. So this is the entire engineering part, the building part of it is actually being done. And you know very quickly about gravitational waves. I'm not going to talk about gravitational waves today, but this is also a way of finding black holes. And when the Nobel Prize was given 3 years ago for gravitational waves, I can give another talk on that sometime later. Even at that stage, 40 authors from Indian institutions were part of the 1,000-author paper that produced the first gravitational wave, LIGO. And now, and that comes from, again, this Einstein's way of looking at gravity, except that instead of the distortion of space-time, we are actually detecting the waves, the ripples of space-time. And it is now, so if, for example, the size is of the order of, again, I've dropped. No? Can you see my thing?
Yes, sir. Yes, sir. We can see that.
Yes, sir.
Okay. And so in this particular event, 230 times the mass of the sun, black holes merging to form a 60 times the mass of the sun black hole, which is the size of it is of the size of about a state of India almost, the Schwarzschild radius. So what is happening now is that we now, from the LIGO experiment of the 2 LIGO observatories in the US, we have been able to measure 50 such events. And each of these events, the gravitational wave detections, you get 2 black holes merging into a third one. So you detect 3 of them. And the most interesting thing is, in the last detection that happened before the lockdown, we again, but up to now, this is what we have found. I had a ding again. Am I still there?
Yes, sir. Yes, sir.
Yes.
There is a sound that keeps saying that my connection is dropped, and sometimes there's a different sound come. Anyway, so if you look at this particular plot, this is actually one of my last plots. You will see that these are the masses of the black holes that have been detected till now from everything. The purple dots, and on the y-axis is the...
Yes, you are back. But you are muted, sir.
Yeah. So let me stop talking about what I was saying. My last slide was a bunch of books that people can read on black holes and on Einstein's life, and I shared that. And I just wanted to end the talk there. Thank you very much. I'm very sorry. I think there's a big storm going on outside.
Yeah.
Looked out the window, and maybe that is why we are, my connection is failing.
So do you have the storm also? We are going to have one.
Maybe that we are having it at both ends. Anyway, so let me just stop presenting and see whether people have questions. I'm very happy to talk. Then I.
There are a number of questions, sir, in the chat box.
Can I ask one question?
Yes, go ahead, please.
Yeah. First of all, just I
can also see the chat box.
Yeah, because you see that according to de Broglie's hypothesis, every matter wave has an antimatter. So if black hole exists and if black hole is a matter, then do we have the anti-black hole? Because de Broglie's hypothesis cannot be violated. Every matter wave has got antimatter wave. So black hole exists means it has got a matter wave because it exists. So do you have the anti-black hole?
Well, that's a very interesting question. But as you know, this asymmetry between matter and antimatter is a big mystery in theoretical physics. because even though theoretically you can see that, so all particles should have antiparticles.
Yeah.
That's what the theory said. But if you look at the real universe now, you see that the amount of antimatter is very, very small. The amount of matter. So this asymmetry between matter and antimatter is a big mystery in theoretical physics. At some point in the early universe, something happened to cause this asymmetry, and we don't understand that. So actually, in the current universe, the amount of antimatter is very, very small.
Okay.
You can create that in particular.
Yeah. Conceptually, it can be there, but we have to physically observe that by the laws of physics. That is it really true?
You can have. Can you hear me? You can have an
Yeah.
anti-black hole, in a sense, what is known as a white hole, which means that you can, because the equations of physics are all reversible. So as soon as you have something in which nothing can escape from, you can actually have the opposite of that.
Hello, sir. Hello, sir.
That is allowed again by theory.
Okay.
But it is impossible to see how that is going to actually happen.
I think, Otonu, the connection is not working properly.
Yes, exactly, madam.
So
what we can do, we can post these questions to email the questions, and we'll ask for the reply.
The question. So as soon as he comes back, why don't you present the memento and
Yes.
So can you send the PPT, sir?
So we'll request Dr. Raychoudhury to give us.
Okay, sir.
and moreover, we are going to put it up in our YouTube channel. It's getting recorded, so you can see from there.
In fact, actually, to the audience, I would like to mention that I am fortunate to present in the meeting because I am also a student of Professor Amol Raychoudhury and his fellow, Professor Amitabh Raychoudhury, who taught us the complete this thing, and we learned the cosmology from the theory of gravity from the Amolendu Raychoudhury, and we did the work on the time arrow, which Ortega's reciprocal relation in the universal thermodynamic equilibrium applied in the case of the biological genetic sequence. So this is really a very good lecture, and hope that the IEEE section should organize such kind of innovative talks by renowned speakers.
Otonu, he's not yet back.
Yeah.
Why don't you call him and tell him to...
he's not picking up my call. Maybe mobile is not with him.
Come back.
He'll come back, I guess. He's back.
Yeah.
Sir, what we can do?
See, what we thought is we'll email you the questions because it's getting very complicated. So, and somebody was asking if you would like to share the slides or something.
Sir, you are muted. Sir, you are muted.
No, he's not muted.
Oh. Sir, your voice is not coming somehow.
Can you hear us?
Yeah, I can hear you. Can you hear me now?
Yes.
Oh, yeah,
yes,
now we can hear.
Yes, sir.
This is very interesting because I do at least 5 or 6 such events all week, and this does not happen. So today is a very unusual day.
So this is God intervening.
And it is not God. It's a pretty bad storm going on outside.
Yes. We are going to have that.
Right. Anyway, so yeah, I'm sorry and thank you for your patience. A lot of people stuck with me to the end. I am available for another 10 minutes or so. If you can ask me questions, I'm here.
So may I ask you a question?
Yes, please go ahead.
It is really a very interesting topic. Now, I would like to ask you one thing that, as you were saying, that black holes, essentially they are black, right? So how do we identify between stellar mass black holes and supermassive black holes?
No, I didn't understand your question.
Means,
You
means,
don't see the black hole, right? So you don't see the black hole. What you do is you find the effect of the gravitation of the black hole, and as a result, you can measure its mass, right? So I showed you how the orbits of the stars around the central black hole of our galaxy, you can, from their orbits, measure the mass of the black hole, and that gave you the mass, which is a few million times the mass of the sun, and that is indeed the range of the supermassive black hole.
okay.
Similarly, from the X-rays, I showed you how you could measure you could detect and then measure those point objects, the accretion disks around the black holes. If you model those, you get straight away the mass of the black hole that's causing that kind of radiation, and that tells you. So I showed you at the end. I don't know whether you missed it, or I missed showing it, but a plot of all those masses measured from gravitational waves, from X-rays, etc., of 60 times the mass of the sun, 40 times the mass of the sun. So those are stellar mass black holes. We are measuring the mass, and so the way the ways in which we detect the black holes also give us a way of measuring their masses. I hope that's all right.
Yeah.
Anybody else?
Yeah,
So we have got so many questions. What we are planning, we'll email you the questions.
Yes.
And okay. And
yes, and
thank you very much for this amazing lecture. We enjoyed every bit of it. And when you are disconnected, we are waiting patiently. We'll organize once again such talk. And
maybe
we'll
on
invite you.
gravitational waves as you
I'll
suggested.
be very happy to come back, and I'll make sure we do it on a night when there is no storm.
Yeah. And
But you cannot predict it so much in advance.
Well, science tells us that. I knew that there was a storm coming today. It is
No,
not
but when
a.
we decided on this date, that was quite far back.
Yeah, it's true.
And
So please display the images that we have.
So
It's really beautiful.
On behalf
The
of
lecture
IEEE
was, yeah.
on behalf of IEEE Kolkata section, we want to present a memento. It's called a green memento.
Thank you very much. That is fantastic. This looks absolutely stunning.
Yeah.
So you can go and take rest under your grove of trees someday.
Excellent. Well, I need an apple to fall on my head, or maybe a mango.
Thank you once again for this wonderful lecture. I also want to thank all the participants for joining in this webinar in amid of such pandemic and difficult situation. Thank you once again.
Thank you, and I'll see you again.
Yes, sir.
Okay. It was almost 100 people joined the program, so it was a beautiful lecture. Yeah.
Very nice. I can see Raychoudhury has written in the chat box that you put it on a big screen. That is amazing.
Yes. Actually, 3 of us listened to you.
Very nice. Thank you very much. It was very enjoyable. I mean, if the connection didn't play up, it would have been great.
And we are very sure that University of Birmingham and Presidency University missing a very good teacher.
Thank you. I'm glad that so many people turned up today.
Yeah.
And,
it cost 101.
Thank you.
Actually, we want to have another lecture in continuation of today's lecture.
We'll do that. I mean, I think I can certainly.
So could you think of which month would be nice? I mean, can you predict in advance? Let's say July or June.
Look, tomorrow it will be different, right? Because as I said, I'm giving 5 or 6 lectures. I mean, I'm teaching on this. So,
No, I mean July.
that doesn't really happen. But
July.
July would be all right. July, August will be okay.
Okay,
July,
so then
August
we
will
think up some Saturday in July.
Yes, that'll be nice. I can do. Thank you.
Thank you.
Okay, bye for now. Thanks.
Bye.
Bye.
ঠিক আছে, Autonomo. So thank you all for being with us.
Thank you.
Thank you.
Thank you very much.
Thank you.
So Autonomo, somebody wants the feedback link or some. You have to take the questions and send to someone.
Okay, I'll email the feedback link. Huh?